Okay, we have a few more joining, so as soon as I get most of you admitted, I'll go ahead and begin. One waiting to join. Okay, I'm going to go ahead and share my screen. Okay, so what we're going to do today, I'm going to review. You have a test on Friday. That test will be online, and I'll send out more details about that. Okay, so I'm going to go through a review. There won't be very much from chapter 1. There'll be some. Okay, the structure of the atom. Okay, I'm not going to say much about that on the test. We might have one question about electron configurations. So I'm going to move pretty quickly through that. Okay, be sure you know the number of valence electrons for a given element. Okay, so I might ask you something like that. Lewis dot structures for atoms and then later for molecules. Recognize which compounds would be ionic and which would be covalent. Understand the difference, the definition of electronegativity. Okay, so in this electronegativity chart, okay, those elements that are widely separated in the periodic table are likely to be ionic. Okay, for example, let's take calcium chloride. Okay, calcium is way over on the left, chlorine is way over on the right. Okay, there's going to be a large difference in electronegativity, so this is clearly ionic. It's a alkaline earth metal and a non-metal. Okay, if we have a compound made up of elements, two non-metallic elements, those that are closer to the center of the periodic table. Okay, for example, carbon disulfide. Okay, that's going to be a covalent because there's not a lot of difference in electronegativity between carbon and sulfur. Okay, and then review this. This is the distinction, the arbitrary dividing lines between nonpolar, covalent, polar covalent, and ionic. Okay, and these numbers represent differences in electronegativities. Okay, let's go back. Ionic bonds involve the transfer of an electron or electrons. So we have fully charged ions, and they're held together by electrostatic attractions. Covalent bonds involve the sharing of electrons, and polar covalent bonds involve unequal sharing. If you haven't done so already, make sure that you complete Chapter 1 of Pushing Electrons. That's a good tutorial on how to draw Lewis structures and how to determine formal charges. Okay, so I might ask you about which correct and incorrect Lewis structures. Okay, anything in the second row of the periodic table cannot exceed 8 electrons in its valence shell. That's what we call the octet rule. Okay, so carbon can't have 5 or 6 bonds, neither can oxygen. Okay, here are some common bonding patterns. For neutral molecules, hydrogen always has 1 bond, nitrogen has 3, oxygen 2, halogens have 1 bond. And they have 0, 1, 2, and 3 unshared pairs of electrons. Be able to calculate, recognize, determine formal charges. Pushing electrons, as I say, is a good tutorial for that. VSEPR, okay, will definitely be some questions about VSEPR. VSEPR says that electron pairs, whether they are bonding or non-bonding, are localized into regions of space, into orbitals, and they repel each other. They want to get as far apart as they can. If you have 4 electron-rich groups, okay, the ideal bond angle is 109.5. 3 electron-rich groups, as shown here with ethylene and formaldehyde, it's a trigonal planar, 120 degrees. And 2 electron-rich groups would be a linear geometry. Examples being carbon dioxide and acetylene. We have to take into account unshared pairs, as in ammonia and water, in determining the shapes of molecules. Okay, a few minutes ago I talked about polar bonds. We can have polar bonds but have a nonpolar molecule if the dipoles cancel each other out, as they do in carbon dioxide. Okay, so that has polar bonds, but it's a nonpolar molecule. Water, because of its shape, is polar because of its bent geometry. It has a separation of charges. So is ammonia. Ammonia is a polar molecule because of its trigonal pyramid geometry. Okay, just more examples of polar and nonpolar molecules. Okay, I'm going to have a couple questions about resonance. Next week, I'll give you, my plan is to give you a quiz about resonance, and I want to give you the opportunity to complete Chapter 2 of Pushing Electrons. Okay, this is a difficult concept, but it's also something that we're going to be using throughout the rest of the course. In resonance, only the electrons can move. Okay, all of the contributing structures have to be valid Lewis structures. Not every molecule or ion will exhibit resonance. Okay, here we have the resonance forms for the carbonate ion. Okay, point one, we can't gain or lose any valence electrons. All the resonance contributing structures have to have the same number of valence electrons. None of them can violate the octet rule, although some third period elements, such as phosphorus and sulfur, can have up to 12 electrons. And they differ only in distribution of valence electrons. They have the same number of paired and unpaired electrons. Okay. Okay, in your first year chemistry course, you learned about atomic orbitals, s orbitals, and p orbitals. S orbitals have a spherical shape. P orbitals have this figure 8 or dumbbell shape. There's 3 of the 2 p orbitals. They're 90 degrees apart from each other. And okay, in describing geometries and reconciling molecular geometries with atomic orbitals, a hybrid atomic orbital model was developed. The main thing that I'm concerned here is not whether you can derive these, but be able to associate a particular hybrid with a particular shape. Okay, SP is linear. SP2 is trigonoplanar. SP3 is tetrahedral. Okay, and these include bonding and non-bonding pairs. Okay, the 2 main kinds of bonds that we're talking about in this course are sigma and pi bonds. Sigma bonds result from direct head-on overlap. Okay, that's what we have between the 2 carbons. And then pi bonds result from side-to-side overlap. In pi bonds, 2 lobes are overlapping. Okay, and there's a couple of different representations here. If we have a triple bond, okay, as in acetylene, there's 1 sigma and 2 pi bonds. That's where we get the 3 bonds. Oh, functional groups. Okay, this is going to be really important. Okay, be able to, okay, if I show you a drawing of a structure, okay, you've got to be able to identify the correct functional group. Okay, and okay, for example, OH, if I were to draw ethanol, for example, identify the functional group, okay, that's an alcohol. These are examples of amines. Okay, aldehydes and ketones. Make sure you recognize the difference between aldehydes and ketones. Aldehydes and carboxylic acids often get confused. The carboxylic acid has an extra O. Okay, it's C double bond O, OH. The aldehyde just has an H. A ketone has carbons on both sides. Okay, so here's the carboxylic acid group. And then I also, in one of the recorded lectures, I also went through several other functional groups, okay, such as esters, amides, ethers, and the sulfur compounds, for example. Okay. Okay, so I'm going to exit out of this. And then I'm going to, let's go on to chapter 2. Okay, so from chapter 1, again, not a lot about electron configurations or the structure of the atom. As I say, functional group is going to be really important. Shapes of molecules. Okay, I may ask you about shapes of molecules. Correct Lewis structures. Covalent versus ionic. Okay, chapter 2, acids and bases. Okay, I won't ask you about the Arrhenius definition. We're not using that at all in this chapter. Bronsted, Lowry acids and bases. Yeah, that's an important part of organic chemistry. Okay, an acid is a proton donor. A base is a proton acceptor. Okay, be able to recognize conjugate acid-base pairs, for example. Okay, so when HCl loses a proton, it loses both an H and a plus. So the conjugate base is chloride. When water accepts a proton, it gains both an H and a plus. Okay, so it becomes H3O plus. Here is the introduction of curved arrows. Okay, we're going to be doing a lot of this throughout the course, but this is just one example. Curved arrows show the movement of electrons. The spontaneous direction of, well, actually, let's back up. The main point I want to make here is the stronger the acid, the weaker its conjugate base. The stronger the base, the weaker its conjugate acid. Okay, so these are conjugate acid-base pairs. An acid can be positively charged, neutral, or negatively charged. These are some examples. A base can be negatively charged or neutral. Okay, I can't think of any examples of those that are positively charged. Because of species is positively charged, like NH4 plus, it's going to repel an H plus ion. Diprotic acids can give up 2 protons. Triprotic can give up 3 protons, one at a time. And understand the distinction between strong acids and weak acids. Okay, so a strong acid is one that completely or almost completely ionizes to form hydronium ions. Okay, these are strong acids. There's only about 6 of them. Okay, these are some of the strong bases. Okay, there are, of course, bases that are stronger than hydroxide. A weak base and a weak acid are those that are incompletely ionized in water or incompletely ionized in general, not necessarily in water. The Ka is the equilibrium constant for the ionization of a weak acid. The larger the Ka, the stronger the acid. pKa is minus the log of the Ka. This goes in the opposite direction from the Ka. Okay, so a small Ka would result in a large pKa. So FH is an extremely weak acid. Its pKa is 51. Its Ka would be 10 to the minus 51 power. Okay, and then down at the bottom you have the strong acids, okay, such as HI and HBr. Okay, their pKa's are large negative numbers. So hydrogen bromide would have a Ka of 10 to the 8th. Okay, since its pKa is minus 8. The direction of an acid-base equilibrium is always from stronger to weaker. Okay, it always favors the weaker conjugate acid-base pair. Okay, some of the things that affect the strength of an acid: the electronegativity of the atom bonded to H, resonance stabilization of the anion, inductive effect, and size and delocalizations of charge. Okay, so going across a row, as we go from CH to NH to OH to HF, the difference in electronegativity between that atom and hydrogen increases, so acidity increases. Okay, we could say the same thing for the next row. SiH4, pH3, H2S, and HCl. HCl would be the strongest, then H2S, and so on. Okay, resonance stabilization. Okay, it's a big factor. Acetic acid, which is an example of a carboxylic acid, forms the acetate ion. Well, the acetate ion can spread that negative charge between both of those oxygens, and that's a highly stabilizing phenomenon. Okay, when an alcohol, such as ethanol, loses a proton, we get the alkoxide, or ethoxide ion in this case, and that negative charge has nowhere to go. It's fixed on the oxygen. That's where it has to stay. And so there is a difference in pKa values roughly of about 11. Okay, so this is acetic acid is 10 to the 11th times, 100 billion times more acidic than ethanol. Okay, so this shows the resonance stabilization of the acetate ion. In fact, several of the strong acids like sulfuric and perchloric and nitric all have anions that are resonance stabilized. Okay, a while back, a couple slides ago, I said that going across a row, comparing neutral species, acidity increases. Okay, for example, HF is more acidic than water, which is more acidic than ammonia. Going down a column increases the acidity. Okay, so in the hydrogen halides, HI is actually the strongest acid. Okay, so I might ask you about comparisons of which one is the strongest, which one is the weaker acid. All right, Lewis acids. At this point, I'm just asking the definition. This is actually going to be a really essential part of the rest of the course. This is pretty much how all of, or almost all of our organic compounds are going to react, is by Lewis acid-base reactions. But by this model, a Lewis base is an electron pair donor. An acid is an electron pair acceptor. Okay, and Lewis acid-base reactions don't even have to involve a proton, although the proton is an example of a Lewis acid, but it's actually much broader than that. Okay, so here is the proton accepting a pair of electrons. Oxygen is donating a pair of electrons. Okay, because hydrogen would have too many electrons when it accepts that pair, it has to give up this pair to chlorine. Okay, so that makes the chloride negative. Okay, here's a similar example with methanol and HCl. Some common Lewis bases. Okay, most of these will either have a non-bonding pair of electrons. Okay, the only examples not shown are those that have a double or triple bond. You can donate a pair of electrons from a double or triple bond. But all of these that have a non-bonding pair of electrons. Okay, so let's move on to chapter 3. Okay, alkanes and cycloalkanes. Okay, I discussed this in terms of functional groups, so be aware of these, know these terms, what a hydrocarbon, what a saturated hydrocarbon is, okay, what an alkane, and an aliphatic hydrocarbon is another name for alkane. Okay, here's the 4 classes of hydrocarbons. This chapter specifically dealt with alkanes. Okay, alkanes have only single bonds. The carbons have a tetrahedral geometry. Okay, associate tetrahedral with sp3. Okay, be familiar with how to draw line angle formulas and how to interpret them. Okay, know from memory the first 10 alkanes and how many carbons they contain. CN, HN plus 2, okay, be aware of this general formula. Okay, know what constitutional isomers are. Okay, they have a different carbon skeleton. Okay, here is butane and commonly called isobutane, but by the IUPAC it's 2-methylpropane. These are, they have a different carbon skeleton. Okay, as the number of carbon atoms increases, the number of constitutional isomers goes up very quickly. Okay, make sure that you know and recognize all of these alkyl substituents. Okay, on this table. Okay, be able to name a structure using IUPAC. Then I'll also ask you questions in the other direction. I'll give you a name and be able to identify or draw the structure. Just a quick review. The parent is the longest carbon chain. Every substituent gets a number, even the same substituent on the same carbon. Okay, we want to use the lowest set of numbers. Okay, so this compound down at the bottom of the page is 2-methylpentane, not 4-methylpentane. Okay, if I ask you to draw 4-methylpentane, you could do it, but it wouldn't be the correct structure. Okay, just some more examples. The lowest possible number. If we have the same substituent occurring multiple times, we use prefixes like di and tri. So this is 2,4-dimethylhexane. List substituents in alphabetical order. And, okay, classification of carbons. I might ask you to identify classification of carbons according to how many carbons are directly bonded to them, okay, whether they're primary, secondary, tertiary, or quaternary. So this is a quaternary carbon. It's directly bonded to 4 other carbons. Here we have a secondary, directly bonded to 2 other carbons. This is a tertiary. And then on the end, we have a primary carbon. Cycloalkanes are not isomers of alkanes because they have a different molecular formula. Okay, remember alkanes were CnH2n plus 2. Cycloalkanes are CnH2n. Okay, and they have the prefix cyclo. And I want to emphasize this. If a structure is not cyclic, don't use the prefix cyclo. Okay, I say that because that's a very common mistake. If it is cyclic, you do need to include the cyclo prefix. Okay, so these are examples of names of cyclic alkanes. Okay, for a monosubstituted cycloalkane, we don't need a number. Okay, as is the case with isopropyl cyclopentane. If we have a di or tri or more substituted cycloalkane, okay, we want to use the lowest set of numbers, and we want to alphabetize. Okay, this is kind of strange, but tert-butyl is under the B's. So tert-butyl comes first in the alphabet, then methyl. While tert-butyl is alphabetized under the B's, isobutyl is actually alphabetized under the I's. Okay, so propane is a 3-carbon alkane, so cyclopropane is a 3-membered ring. Okay, I'm going to skip over this. We'll come to these suffixes as we talk about the appropriate functional group. Okay, conformations. Conformations are not actually isomers, but they're rotational forms that result from the free rotation about single bonds. Okay, be able to interpret Newman projections. Okay, so this is the Newman projection for the staggered form. Okay, we're sighting along the carbon-carbon bond. The bonds coming out of the center represent the carbon in front. Those that go out from the edge of the circle are those on the carbon in back. Okay, in the staggered conformation, the CH bonds are as far apart as they can get. In the eclipse conformation, that's the highest energy form conformation. Okay, here they are eclipsed, and we have what is called torsional strain, where there's repulsion between these hydrogens. All right. Then we looked at conformations of cycloalkanes. In cycloalkanes, you can have both torsional and angle strain. In angle strain, the carbon atoms are forced to deviate considerably from the ideal of 109.5. Okay, with cyclopentane, there's very little angle strain. Okay, but if all 5 carbons are in the same plane, there is torsional strain because of eclipsing of hydrogens. Okay, and so that is relieved by puckering the ring into the envelope conformation. This relieves torsional strain, but angle strain is increased very slightly. Okay, so the decrease in torsional strain is greater than the increase in angle strain. So that's a stabilizing conformation. Okay, the cyclohexane, the most stable conformation is the chair. Okay, in the chair, we have 6 axial and 6 equatorial hydrogens. All right, this is the boat conformation. In the boat conformation, let me back up for a minute. In the chair, there is no angle strain. There's no torsion, or there's very little torsional strain because the hydrogens are staggered. In the boat conformation, we have eclipsing of hydrogens, and then we also have torsional strain from these 2, what are called flagpole hydrogens. Okay, torsional strain is a bending force on this bond right here. All right, if we have substituents on a cyclohexane ring, okay, generally, they're going to prefer to be equatorial rather than axial. Okay, in methyl cyclohexane, which is shown here, the methyl flips back and forth between equatorial and axial, but the favored form is the equatorial. Okay, there's a difference of 1.74 kilocalories per, or 7.28 kilojoules per mole. Okay, the larger the substituent, the greater the preference for equatorial. Something like a tert-butyl group has to be equatorial. In fact, a tert-butyl group will effectively lock the ring. Okay, cis-trans, be familiar with cis-trans isomers of cycloalkanes. Okay, these are distinct from constitutional isomers, because in constitutional isomers, the substituents have different positions. In cis-trans or geometric isomers, the substituents are on the same positions, but they have a different 3-dimensional arrangement in space. Cis-trans isomers cannot be interconverted by rotation or ring folding. Okay, so here we have cis and trans 1,2-dimethyl cyclopentane. Okay, these are not constitutional isomers because the methyls are in both of these structures are on 1 and 2. If we had 1,1-dimethyl and 1,2-dimethyl, those would be constitutional isomers. Okay, these are geometric or cis-trans isomers. The only way we can go from cis to trans is to break a bond and then reform it in a new location. Okay, so these are 2 ways of representing the 3-dimensional geometry of these cis-trans isomers. You can show it like this, or you can show the dashes and wedges. Okay, so this means that both methyl groups are back. There's also a hydrogen that's forward that's implied, that's not shown on each one of these. Okay, here's the trans. Again, there's a hydrogen going forward that would be a solid wedge on this carbon. And then there's a hydrogen going back, which you would represent as a dashed line. Okay, these are different compounds. They have different properties. Okay, and here's a couple of other ways to represent trans and cis cyclohexane isomers. Sometimes it's represented as a planar hexagon, even though in reality it's not really a planar hexagon. Okay, I said earlier the most stable conformation is the chair. Okay, so here is trans 1,4-dimethyl cyclohexane. Okay, I think it's pretty easy to see that the structure on the left, where both groups are axial, that's trans. Okay, when we do the ring flip, it's still trans. Okay, but you might look at the hydrogens here. Okay, this one on the left is straight up, the one on the right is straight down, so again, it's still trans. Okay, sometimes it's harder to recognize cis and trans when the groups are equatorial. Okay, there's a substantial difference in energy stability between these two equilibrium forms. The diequatorial is more stable. Okay, for the cis 1,4, here we have one axial, one equatorial. When we do the ring flip, we still have one axial, one equatorial. And so they're both the same energy, right? Okay, so they have equal stability. Okay, the trans, okay, had both methyls axial or both methyls equatorial. So to go from the trans, which was on the previous slide, to the cis, okay, that would have involved, for example, removing a methyl here and moving it down to the lower position to go from trans to cis. Okay, so this was an example we did. You might have a question like this. Okay, so here is the hexagon form. So be able to identify the chair and which one of these methyls are in the axial and which ones are in the equatorial positions. Okay, and then okay, I'm going to ask you about physical properties. Okay, alkanes are nonpolar compounds. The only significant intermolecular force is London dispersion. Okay, because alkane molecules interact with each other by these weak London dispersion forces, they have low boiling points. Those with 1 to 4 carbons are gases at room temperature. 5 to 17 carbons are liquids. And then those 18 and above for a number of carbons are typically waxy semi-solids like paraffin wax. Again, because of the weak interaction between molecules, alkanes are less dense than water. The average density is about 0.7 grams per milliliter. Okay, remember, water is 1 gram per milliliter. Okay, so they'll float on water. The liquid and solid alkanes will float on water. Branching lowers the boiling point. Okay, that's an important point to remember. Okay, recognize the sources of alkanes and the products that we get from petroleum. Okay, these are separated by fractional distillation, okay, which represents differences in boiling point ranges, I should say. The residue that is not distilled is asphalt. Okay. Coal is another source of products such as methanol. When it's used to make carbon monoxide, which is then used to make methanol, which can then be converted into a variety of other products. Okay, and then that is it. Okay, and as I say, I'll be sending you the details about the exam on Friday. It will be online.
Will we not have class then?
Right, yeah. We won't meet Friday. You'll just be taking the test.
Do we have to take it at 8 o'clock?
What?
Do we have to take it at 8 o'clock?
I think I'm going to allow some flexibility. Okay, there may be a time limit, but there'll probably be some flexibility as far as your start time. And then there'll also be a later limit. Okay, you can't log in after this time. Okay. Okay, so I'm going to end the meeting for those on Zoom.